this video, I will talk through the 2024 Higher Chemistry paper and explain how I would approach each question, starting off with the multiple choice. Question 1 is asking us about the trends in the periodic table. Sodium and chlorine are in the same period. This means the differences in their ionization energy will be to do with the number of protons in the nucleus, and that makes the answer C for question 1. If they're in the same group, it'd be the number of shells that would cause the differences in ionization energy and other properties. Next one is asking us to predict the state of francium at 30 degrees. Again, data booklet will help us for this. Francium is an alkali metal that comes after cesium. Looking at the melting points and boiling points down the alkali metals, the melting point and boiling points decrease as you go down group 1. That means it's likely to have a lower melting point than 28 and a lower boiling point than 671. This means that at 30 degrees it will have melted, narrowing us down E or D. Covalent radii, again go back to the data booklet. Covalent radii is increasing as you go down group 1, therefore it's likely to be greater than 238. And that brings us to an answer of D. So the data booklet is a big help for that one. In this one, they're asking us about pure covalent bonds. This can also be called a non-polar covalent bond. In this case, there is no difference in electronegativity. We want to go to the data booklet and find the values for each of them. Only phosphorus and hydrogen have the same values, and that would be the one that contains the non-polar covalent bonds. All the other ones would contain polar bonds. In this one here, we have two reactions. We have got an oxidation and we have a reduction. First, before we can combine them into a redox, must have the same number of electrons in each of them. This means we want to take the first equation and multiply it by 5, and the second equation and multiply it by 2. Then if we look at the two left-hand sides together and the two right-hand sides together, we can see that we can cancel out the electrons. That leaves us with the combined equation as shown. They're asking us about iodide, which is our I-. They're also asking us about permanganate, which is the MnO4. The ratio between the two of them is 10:2 or 5:1. So 1 mole of permanganate would oxidize 5 moles of iodide. To save ourselves a little bit of writing, we wouldn't have to write out the combined equations. Once we have the two scaled up versions, we will still see that it's got a 2:10 ratio here. But if you're asked to write out the full equation, you would have to do that bottom line. So it just depends on the question. Next question, we're asked to look for the most likely oxidizing agents. Page 13 is going to help us a lot with this. On page 13, at the top right are the strong reducing agents. And then the bottom left is where we find our strong oxidizing agents. You then find the 4 chemicals that are mentioned. The most bottom left of these options is iodine I2, and that would be our correct answer here. For number 6, we're asked about isomers. They would have the same molecular formula but different structural formula. To half our options, if we count how many carbons are in our given chemical, we can see which ones of the options have the same number. So we'll get 2 carbon branches. Another one here, carbon there, carbon there, carbon there. 1, 2, 3, 4, 5 carbons in total. Methyl is a 1 carbon branch, and butyl would have 4. So this is a option as the answer. Second one as well would be an option because there's 5 carbons. Next one, we've got 1 plus 5, so there's 6 in total. Not going to be that. And then C and D are just rearranged versions, so they will not be the correct answer as well. What is likely to happen here is one of these names will be for our chemical we are given. If I start to sketch this out, we have a carbon with a hydrogen, then we need 2 CH3 groups. So CH3, CH3, and CH. That's me done that part and that part. We then need a carbon with 2 hydrogens. That's us here. And then we've got our carboxyl group, which is C, double bond O, O, and H. We look for the longest chain of carbons, which in this case would be 4, so butanoic acid. In this one that's given, we have our methyl group on the 3rd carbon, which means an isomer has to be different than that, which means A would be the correct one, because in that one, we would shuffle along the carbon branch onto the 2nd carbon. Next question, we're talking about an alcohol that reacts with acidified potassium dichromate. One fact that we need to know is that primary and secondary alcohols would react with oxidizing agents. In this version, it cannot then be E or D because they're tertiary ones. To decide if it's got single bonds between carbons only, or it has at least one carbon-to-carbon double bond, we'll draw it out. If I draw out with all single bonds between the carbons, we would have something like this. And in this one, we have got C4, we've got 9 H's, as well as the OH. Only way we could need just the 7 hydrogens is if I put in carbon-to-carbon double bond somewhere in the chain. I can get rid of 2 of the H's, and that knocks that down to C4H7OH for that one. So it must be unsaturated. You need just 7 hydrogens. So sketching them out will help get you to the answer there. We're looking at relative rate in this question. That is one of the 2 rate relationships that you may be asked to use. The relative rate or reaction rate equals 1 over the time. Most typically, we will do time in seconds. 3 minutes is 180 seconds, plus the 20 gives you 200 seconds. And that comes out as 0.005. For the units, it was 20 seconds. The units will be per second, s to the minus 1, and it gives us an answer of A. In number 9, they're talking about alpha amino acids. They give us the description of what those are. The amino group is on the carbon next to the acid group. Step 1 for me would be to identify all of our amino groups. Amino is NH2. Could be NH if it's done with 2 carbons joined to it, but in these ones they're all just NH. We've then got our carboxyl group, which is the QCOOH, C double bond OOH. And they are saying we need that amino group is on the carbon next to the acid group. So we look for the acid group, we look for the carbon next to it. We don't have the amino group on that carbon, so it's not our answer. Next one, we do have the carboxyl group on the carbon next to the amino group. And our next one, we're 2 separated away, or actually both of them, of the next ones. These will not be alpha amino acids, so B was the answer for question 9. On to number 10. Here, we're looking at isoprene units. They contain 5 carbons. Not sure how clearly this will come out, but I'll just mark it with a colored highlighter. So here, we have got our 5 carbon group. Here, we've got 5 carbons. Here, we've only got 4 carbons. And here, we've got 4 carbons. That narrows us down to just A or B. When we are forming terpenes, which are the chemicals made from isoprene units, it will be 2 or more isoprene units joining together. If we look at in B, the bits that are left over are all separated apart. That's not how terpenes would form from isoprene units. We would have them joining together, one isoprene unit joining onto a second. So the rule of 5 can narrow it down. And then you want to look for one where when you split it into the bit that's highlighted and not highlighted, you've got 2 of these 5 carbon groups. Is correct for that one. On to the next one. We're dealing with the iodine number of an oil. The mass of iodine can react with 100 grams of oil. And it's through carbon-to-carbon double bonds. It says at the top that carbon-to-carbon double bonds can undergo addition reactions with iodine. If we go for just say the biggest one first of all, go for linseed. So linseed contains the most carbon-to-carbon double bonds. Another way of saying that is it's the most unsaturated. Double bonds prevent the molecules from packing closely together Because they're not closely packed, it would be weaker intermolecular forces, lower melting point, therefore it's more likely to be a liquid. And we were actually to get the one that's the lowest melting point, so linseed would be the best option there. If you'd picked this up the smallest one, we would say that olive oil has the lowest number of carbon-to-carbon double bonds. It's the least unsaturated. It would be more tightly packed. It would have stronger intermolecular forces. It would have a higher melting point and more likely to be solid at room temperature. I just lucked out with the one I picked of the two extremes. Next one, we are looking at removing water in a dehydration reaction. Show you what's happening. We are removing the hydroxyl OH group, and then we're taking either this hydrogen to the left-hand side, making but-1ene, or we're going to take the OH with the hydrogen to the other side, putting the double bond on that side. And we need to think about, of the versions they give us, what kind of products could we make? To do it, showing all these steps, draw them out. First one, we have 3 carbons with an OH group on the second. I can take these 2 away, or I can take the 2 on the right hand side. When we do this, that would make a double bond between the first and the second. So this would make propene. Don't really need the 1 because you can't get prop-2ene. This would be the same chemical, and that would mean that they are not 2 different isomers. They are the same alkene, so it's not going to be that one. When it comes to the pentan 3-ol, I can either take away these 2, put a double bond there, making that pen-2-ene. If I take the one to the right hand side of the OH group, that would also be pent-2-ene, just flipped round. Again, not going to be our answer. Moving on to hex, which is 6. You can either take the hydrogen on the left of the OH, put a double bond there, which would make this hex-2-ene, or I could take the one on the right hand side, which would make hex-3-ene. That will be our correct answer. Same as before, we can lose those 2 to put the double bond in the third position, hept-3-ene. But here, get rid of those 2. Again, 1, 2, 3, it would be this same chemical. So we do not have 2 isomers for this one. Not going to be our answer. And C was correct. A bit of a shortcut way would be to look at how many carbons we've got. We've got 4 carbons. And we've got the alcohol on position 2. So we're dealing with even numbers here. In A, B, and D, you have got the OH group right in the middle of an odd number of carbons. In the second position of 3, third position of 5, and fourth position of 7. Whereas the hexane and the butane, they're all off center because you've got an even number of carbons, so there's no one middle carbon, and that allows it to have multiple isomers. So that's the longer way, but you can use that kind of logic to help guide you as well. In this one, we are going from an alcohol to a carboxylic acid. Condensation makes esters and proteins. Hydrolysis breaks esters and proteins. Oxidation of alcohols forms, first of all, aldehydes, ketones. And if it's an aldehyde, then we get our carboxylic acid. And reduction's the opposite. It forms alcohols from those aldehydes, ketones, and carboxylic acid. That leaves us with D as our correct answer. Okay, next one, we're dealing with boiling points. We are dealing with intermolecular forces, which rules out the covalent bonds. We're not breaking the intramolecular forces in that one. If you wanted hydrogen bonding, you would need hydrogen to F, O, or N. Alkanes are hydrocarbons, just carbons and hydrogens, it's not going to be that one. All of the molecules will have LDFs because they contain electrons, and that'll be that one there. Here, you would need to have a polar molecule. However, if you look at the shapes of the alkanes, they are symmetrical shapes, Therefore, they would be non-polar molecules, and you won't have permanent dipole, or hydrogen bonding in those ones there. It is a non-polar molecule, therefore it's LDFs alone. Next one, talking about what a catalyst does. At higher, a catalyst lowers the activation energy. That is the energy needed for a successful collision. That is a true statement, so not our answer. Increases the energy of the molecule, so they're more successful collisions. That is incorrect. This would be achieved by increasing the temperature. Then you provide more kinetic energy to those molecules. In terms of the alternative pathway, this is when we have our reaction profile. When we add a catalyst, it lowers the activation energy, and we have a new line, which I've shown in red. So it does provide an alternative lower energy route. And from baby chemistry, a catalyst does increase the rate of reaction without being used up. That is the correct answer. Yeah. This one here, we are looking at positive and negative ions. We can use the data booklet to help us with these on page number 9. We have got ammonium and we've got phosphate. Ammonium is our positive ion. If I write this out as an ionic equation, we would have NH4 positive, and there's 3 of them, and we've got a PO4 3 minus, which we've only got 1 of. In terms of a ratio, it's a 3 to 1 ratio. So every 1 mole of ammonium phosphate will have 3 ammoniums and 1 phosphorus. Therefore, if I've got 5 moles of ammonium phosphate, I will have 5 times 3 moles of ammonium, and that gives us 15 for an answer of D. If it was asking you about the phosphate, it would be 5 times 1, because there's just 1 of them in the formula, and that would have been B as the correct answer as well. In theory, it could have asked you for all ions, and that's both of them together. So there's 4 ions in total. 4 times 5 would have given you 20 for that. But you have to focus in on the NH4 positive. It says that there. Enthalpy change is the difference between products and reactants. I'll sometimes describe it as the distance between the 2 platforms. The way this question is worded makes it a wee bit more difficult for my usual description. If I just make life easier for us, if I was to say that we had a value of 100 and a value of 50, my usual way to say it would be, well, they're 50 apart from each other, and we're going down from Y to Z, so it's going to be minus 50. But if I was to say it's Y take away Z, so now bring back the letters in, that would have given me 100 minus 50. And then I need to remember to flip it around to negative. So the correct answer for this one would be D, because if I do 50, the bottom value, take away the top value, that does straight away give me minus 50. That's not how I usually think about this. So like I say, I would have probably at first put Y minus Z, incorrectly I might add, but I probably would have started off with that. And just remembering, if it's exothermic, it's going lower at the end, there's got to be a negative change. But from just a mathematical perspective, you'd want to do Z minus Y. So I'd say that's quite a tricky one, the way it's worded. If the numbers were there, it'd be much more straightforward for me. The way it's worded is kind of thrown me a tiny bit. In this one here, we're dealing with Hess's law. And what we're looking at is we are starting at the carbon and oxygen, and we're ending with the carbon monoxide and half of oxygen. We want to do the same journey through the different steps. Instead of going straight across the top, we can go down the bottom and then back up here. Make it easier to keep track of, I'm going to call it delta H1 and delta H2. My arrow in red matches their arrow in black. That means I'm going to use that number just as it is. The second arrow is opposite direction, so I want to minus whatever delta H2 is. Delta H1 is minus 393.5. Take away minus 283. And the minus minus does give you positive. If you prefer to put it in that way, you'd be fine. So you do the minus 393.5 plus the value. There are questions a bit like the one above where it's not numbers, it's the letters. But this way would make that more straightforward. We're adding them two together then to give us minus 110.5 as our final answer. This one, the mean bond enthalpy of nitrogen to hydrogen bond is equal to a third of the delta H for which of the following changes? If that's equal to a third of the overall enthalpy change, that's suggesting that we're having 3 NH bonds are being made. So the only change that's happening is we are creating or breaking 3 NH bonds. If you look at the first one, we've got nitrogen by itself. We've got 3 separated hydrogen atoms, and then we're forming our ammonia. The only thing that's changing is we're joining each of the hydrogens to the nitrogen. That feels like it's going to be our answer because we've got 3 NH groups going on there. Or B, we're starting off with nitrogen, which is triple bonded to itself, and we've got 3 hydrogens which are bonded to themselves. We're making 2 ammonias, which means we're going to be making 6 nitrogen to hydrogen bonds. There's a lot more going on than just having 3 of the bonds being made. Rolling that one out. Here, half N2, 1.5 H2. Again, you need to separate out these things before then joining them together. So there's more changes than just joining 3 N's and H's. And last one, we need to separate that first before we can join together. Our answer is going to be A. Another question, one of the years where one of the differences was at the start was a solid or a liquid. If I had this going to any gas, I have to turn my solid nitrogen into gas nitrogen before doing anything. So that's going to require some energy to warm it up. It's going to mean that there's more changes happening, so it's not going to be that one there. Next one. When at equilibrium, we have equal rates. And it will continue at that rate indefinitely, unless something changes about the conditions. Tells us it's the same conditions, so the forward and backwards reactions will still be equal because they are both unchanged. Is the correct answer there. In this one, this is another Hess's law one. Our target equation, the one that's the subject of all the answers, is A. What I would do is look for each of the parts of equation A in the different equations. Now, each of the 3 equations is only used once. If something appears in multiple equations like the oxygen, we can ignore them and they will sort themselves out from everything else. Next thing we'll do is go through each of the steps one at a time. So the carbon solid is in equation C. It's on the same side in both. It's the same number. Therefore, A equal C by itself. Next up, for the hydrogen, the hydrogens are on the same side. It's the same number, so I'm going to add on D. The HCOOH, the methanoic acid, are on opposite sides, so put it as negative. But it's the correct number, so it'll be minus B as our answer there. And that gives us A. There is a way of proving this by writing out the equations and combining them together. So here I've swapped round B and put the left-hand side on the right and right-hand side on the left. The other two I'll copy as written. Once I've done this, I'm going to consider all the left-hand sides together and all the right-hand sides together. If things appear on opposite sides, they can cancel out. I can cancel out the carbon dioxide. I can cancel out the water. I can cancel out half oxygen with the half oxygen here. Taking the bits that I've not scored out, I have carbon plus hydrogen plus oxygen goes to HCOOH, which matches the target equation at the top. We don't need to do the proof. in one like this, but it's fairly straightforward, perhaps not worth the time and effort to do it. There are some more complicated versions that would require you to consider the equations and how they fit together to see the exact way they all merge together. For that, A is our answer for 21. Here we're dealing with a filtration experiment. It's a bit of a throwback to baby chemistry, S1 and S2 perhaps. We have got our residue is the part that's left over after the filtration's happened, and our filtrate is the chemical that's came through. The solvent would be the chemical used to dissolve the starting materials, and the precipitate would be when a solid forms from two liquids reacting together. In this question, they're asking us about the apparatus to accurately measure 45 centimeters cubed of a solution. In terms of accurately measuring things, a pipette and a burette are both able to measure volumes accurately. A pipette is only good for the one value of volume that's on it. So our pipette would be really good at measuring out 50 centimeters cubed, but that is it. The burette, the one with the tap that you can let chemical out of, that has more flexibility in what value you are measuring out. Although pipettes are accurate, they couldn't measure 45 centimeters cubed. 45 centimeter cubed pipette would be able to do that, but they don't really intend to make them in all the different increments. They would just have set values of 10, 25, 20, 50, whatever it might be. And that makes our correct answer a burette because it's got that flexibility. On to number 24. Carrying out a titration to observe the end point. If you repeat an experiment, you make the results more reliable when you take an average. A white tile allows you to see the colour change more clearly, so you'll know when to stop it. Rinsing the flask prevents contamination, but it's not to do with spotting the end point. And if you ignore the rough titer value, you would average the concordant results, so your rough one is unlikely to be concordant. Next one, we're trying to isolate carbon dioxide. Most suitable method for isolating a gas. So we've got a gas. That if you bubble it through hydroxide, well, calcium hydroxide, that would move water. Not that one. Collection over water, that's the one where you would take your measuring cylinder that's filled up with water. You'd place it in some kind of container which has a little delivery tube coming in from your reaction. Then it would bubble up and collect the gas from that one. That one would work out there. If you evaporate, you turn liquids into gases. And we want a gas out. The gas is already a gas, so let's not do that. And distillation evaporates, then condenses, and mainly used to separate mixtures of liquids. That's not going to be a very good one for that. We want to isolate it. We want to have it by itself. A gas syringe would be even better, more commonly used, but collection over gas would be an appropriate way of doing that. On to the longer answer questions. We're asked about ionization energy, so we go to the page in the data booklet. It shows us at the top what the equations for these are. The first ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. Asked to mention stuff about it being gaseous atoms and removing electrons. Question 2 wants the equation for the first ionization energy of phosphorus. Come back to this page. We are writing E gas goes to E plus gas plus E minus. Instead of E, you put the symbol for the element potass. Phosphorus is P, so it would be P gas goes to P plus gas plus an electron. Next one, we have to compare the melting points of phosphorus and nitrogen. Nitrogen is N2, it's a diatomic molecule. And our P4 is a larger molecule. Those are both part of the covalent molecular section of the data booklet. Other sections include the monatomic elements on the right hand side, covalent network, boron, carbon, silicon, and that leaves the metallic ones. Both of them are non-polar molecules because you can't have polar molecules unless you have a difference in electronegativity. They will both have LDFs between their molecules. Phosphorus molecules are larger and have more electrons in their atoms. This results in stronger London dispersion forces, LDFs. You could tighten up by just saying that phosphorus has more electrons, therefore stronger LDFs than nitrogen. So putting together what are the forces and the strength of them. But those are the points that we make for that. In this question, we're asked to calculate the enthalpy change using bond enthalpies. We first need to decide how many bonds we're breaking. In the first chemical, we're breaking 1, 2, 3, 4, 5, 6 phosphorus to phosphorus single bonds. Let's set that up with breaking 6 times 201, which equals 1206. We're then making 2 phosphorus to phosphorus triple bonds. 2 times 4, 8, 8, which equals 9, 7, 6. When it comes to working out the enthalpy change, we do the breaking minus the making. That's 1206 take away 976, which will equal 230 kilojoules per mole. If you set it up this way, you just do the first one, take away the second one. The reason for that is you need to put energy in to break something, break bond, and when the bonds are made, energy is released. So it's endothermic, the first one takes energy in, making is exothermic, and that's where the negative comes in as well. But like I say, if you do breaking, making, you just take them away from each other, that will make it straightforward. Next one, we're asked to work out the percentage yield. From the data booklet, it tells us a percentage yield equals the actual yield over the theoretical yield times 100. In questions like this, they'll give us two values. One of them is our actual yield, and one of them is used to figure out the theoretical yield. Calcium phosphate is a reactant versus phosphorus, which is a product. We make products, which means our 115.5 is our actual yield that we'll use to work out our final answer. And that means that we're going to just start with the other number, because we dealt with that there. This then becomes one of the typical questions where you have a mass of chemical 1, and you can work out, using the GFM, the number of moles. So N equals 750 over 310.3. And at this point, we want to try and avoid rounding as too much, but I'm going to take it to 2.417 moles. We are jumping from our calcium phosphate over to phosphorus. It's a 2 to 1 ratio, looking at the balance in numbers in front. If there's no number in front, it's a 1. That means we have to half our number of moles to get 1.2085. And then to work out how much we could make of this, we do M equals N times GFM. The number 1.2085 times 124. And I'll take that to 149.85. That can then go in as what we have calculated in theory we could make. Times that by 100 and take that as 77.1% as an answer. Just a term that can be used to describe the action of the carbon in this. Okay, what's carbon doing? An action of carbon. So carbon's gaining oxygen. Carbon's being oxidized. And carbon is reducing. So it's removing oxygen from the phosphate of that. So reducing agent. Other terms that I was going through in my head were things like catalyst, but it's been changed. So it's not remaining unchanged for those ones as well. There's not anything about being limiting factor or anything like that, but it's causing phosphorus to lose oxygen and become separated and be extracted. So reducing agent going to be the answer there. Next one, we're asked to determine the molar volume. The molar volume is the volume of 1 mole. And what are we told? Well, we are told we've got 280 grams, which is the mass. We're told the GFM. So we could work out what the number of moles is. Number of moles equals mass over GFM. So 280 over 28 equals 10 moles. It says that 10 moles occupies 1450 litres. 10 moles is 1450, then 1 litre must be less than that. Nice straightforward relationship. It's dividing by 10. Then we take our 1450, divide that by 10 as well, to give 145. That would be the molar volume for that one. And number 2, we're dealing with different chemical reactions. We're talking about a decomposition. Nitrogen gas produced supplies the energy required for it to occur. Right, minimum kinetic energy required by particles before a reaction can occur successfully is the definition of the activation energy. Next up, calculate the energy released when 80 grams of sodium azide decomposes. That. This is the enthalpy change, which is measured in kilojoules per mole. So what I'd probably do is we'll say, well, that means that 1 mole gives off 42.6 kilojoules. And we've got 80 grams. But 1 gram would be 65 grams. So to follow the same way as before, let's just do N equals M over GFM. N equals 80 over 65. 1, 2. Let's go for 1, 2, 3, 1. 2, 3, 1 moles. 1 moles. If 1 mole gives off 42.6, then 1.231 moles must give off more than that. You go from 1 to 1.231, we can multiply it by 1.231, then that will give us 42 times that as well. Gives me 52.4 kilojoules. Alternative routes to get to the same answer. If you look from left to right, we could times this by 42.6, which would mean we would do the same to 1.231, which is what we did here, just in a different order. Another way I've seen it done is by putting the mass in straight away. So 1 mole of the substance is 65 grams. So 65 grams would give off the 42.6. And we are dealing with 80. If you go from 65 down to 1, because everything through 1 makes it easier, divide by 65, and then times by 80. And that is what we've done here. So I've done it in 2 steps, whereas in this one, what someone would do is do 42.6 over 65 times 80. It'll be ever so slightly different because I rounded doing the intermediate steps, whereas here it's all in the 1. And this one, it'd actually be almost identical. You can still get to 52.4, and that's just 2 different ways from that. Next one, we're talking about sodium azide. State the charge on the azide group ion. It gives us the formula as NaN3, and N3 is the azide. To find the charge on sodium, you can do it in 2 ways. One, go to the electron arrangement. It's 281. It's going to lose 1 electron to become positive. It would be Na+. Or, if you find sodium in the electrochemical series, you can see as well that it's got sodium as a positive ion. If you have N positive, then you'll need to have N3 as being a negative charge. So it would have a charge of -1. In this question, we're asked to balance the equation. If we go through each of the parts in turn and see how many we've got on each side, I'm going to start with the sodium. There's 1 sodium on the left, but 2 sodiums on the right. I put a 2 in front of it here. That then fixes those together. Next up, potassiums. We've got 2 and 1. So let's put a 2 in front of that. That's potassium's now fixed. The nitrogens, we've got 2 nitrogens here and 2 nitrogens there, so that's looking okay. Oxygens, now we had 3 oxygens, now times by 2, so there's now 6 oxygens on that side. Got 1 oxygen there and 1 oxygen there. So only got 2 there. So we need more oxygens on the right-hand side. That. So let's try some numbers then. Now at this point we can go in 2 different directions. If I was to put a 5 in here, that would bump this up to 5. However, I've now got 10 potassiums. So I would need to put a 10 here. But that would have the knock-on effect of messing up the ends. But it would also mess up the oxygens here as well. So I'm leaning towards dealing with putting a 5 in front of the Na2O. That only affects the sodium and the oxygen. We've now got 5 oxygens here, 5 times 1. So the oxygens are now fixed. But to fix it fully, I now need to get 10 sodiums. So I would then put a 10 in front of that. So just go through the count again. We've got 10 nitrogens here and 10 nitrogens there. We've got 2 potassiums and 2 potassiums. 2 nitrogens and 2 nitrogens. 6 oxygens. And then 1 and 5 oxygens gives you 6 as well for that. With questions like this, if you find yourself having to change numbers again and again, so multiple times, you've potentially miscounted. So something I've seen happen quite a lot is dealing with the oxygens on the right side, for instance, thinking it's just 5, is they see that it's 5 times oxygen there and ignoring this one, and that'll throw off your count. You may have to change your numbers like I did here, but if you keep having to change it, you've probably best to start again and reset and see how you get on from there. Next one, we're dealing with silicon dioxide, which has a high melting point and boiling point. Silicon dioxide, there is a difference in electronegativity. It's a relatively high difference, but the maximum difference would be from fluorine to something like potassium, where you've got 4 to 0.8, so you've got 3.2 of a difference. This would definitely be an ionic substance. In this one, the difference isn't quite as extreme as that, so it's more likely to be polar covalent. Based on its melting point being high, this makes this likely to be a covalent network. And then the second thing is that strong covalent bonds are broken when you melt a covalent network. Next one, here we're given a bit of a ratio. We have to work out how much nitrogen gas is formed from 80 grams of sodium azide. Now, we already did the number of moles calculation at the beginning, so I can just still borrow that again. Question tells us that it's a 1 to 1.6 ratio. That means we would take our 1.231 and we need to times it by 1.6 to scale it up the way, because the right hand side has to be bigger. 1.6 times 1.231 and then 1.9696. Keep it as unrounded as possible at first, and then we'll round it at the end. Going over to nitrogen, it tells us that 1 mole is 24 litres. If we have got 1.9696 moles, we're going to do 24 times 1.9696. We'll take our answer from before, times it by 24, and I'll round that to 47.3 to 47.27, but 47.3 litres for answer for that one. Moving on, talking about collisions and why fine powders ensure fast reactions in the airbag. When you break up a lump into powder, you increase the surface area for the collisions to occur on. More collisions, higher chance of successful collisions. That would be that one onwards. Here we get to our first of the 2 using your knowledge of chemistry questions. We're asked to describe ways of telling apart alcohols, aldehydes and ketones. For that, any suitable chemicals and apparatus can be used. Okay, now, key thing here is chemical tests. So melting points and boiling points are not really what we're going to talk about. we want to be using chemicals. First, I want to talk about oxidation of alcohols. So point number one, alcohols can be primary, secondary, or tertiary. And I'll just show a little sketch of each of them. And here I'm using the R group to represent the rest of the molecule to save myself drawing them all out. Primary alcohols are oxidized by oxidizing agents to form aldehydes. And then aldehyde has a carbonyl group on the end of the chain. Secondary alcohols are oxidized to form ketones, where the carbonyl group is in the middle of the chain for that, and tertiary alcohols do not oxidize. Two examples of oxidizing agents that can do this would be copper oxide and acidified potassium dichromate. As of colour changes, copper oxide turns from black to brown and acidified potassium dichromate from orange to green. Leading on from that, aldehydes will react with an oxidizing agent, ketones will not. Oxidizing agents that allow you to do this would be acidified potassium dichromate again, Fehling solution, and Tollens reagent, and those will tell them apart. It would react positively with the aldehyde but not the ketone. In terms of colour changes, acidified potassium dichromate again changes from orange to green. Fehling solution is the one that goes from blue to brick red or red orange, and Tollens reagent will form a silver mirror when it reacts with that. In terms of apparatus, it depends how you've done this in class. You can do it in a dimple tray, you can do it in test tubes, you'd warm up the chemicals and then cause them to react together. We've got procedures, we've got results, and we've got the differences between them as well. So that is, in my humble opinion, better than good. So it'd be worth all 3 marks as well. There may well be other things you can add in as well that I haven't thought of, but this, as it stands, it would pick up all the marks. Next question. We are moving on to talk about proteins. Name the other product when amino acids join to form proteins, such as keratin. To form proteins is a condensation reaction. That means that it would also make water. So amino acids join to form amide links in a condensation reaction, so water is produced. Just a name for the reaction taking place when disulfide bond is formed. So what's happening here? We've got 2 chemicals joining together and we're losing a small molecule. So that could actually be classed as condensation. It's not always water for condensation. So it would be 2 molecules joined together and release a small molecule, usually water. So condensation, probably one I'd go for that. Essential amino acids are amino acids that are not made by the body, so must be obtained from the diet. And that would pick up the mark there. Next one. Air can be straightened using chemicals. A chemical is applied that causes the fibre to change shape. Proteins changing shape is denaturing. They are being denatured. In this one, we're asked to draw one of the amino acids that make up this section of keratin. You need to be hunting for the amide links, which is when you've got C double bond O connected to NH. And in this case, there are 2 of them between the 3 amino acids. Next, you want to pick one of the sections. The left-hand side is probably the most straightforward to draw. I have the benefit of being able to just snip them out, so I'll actually do all 3. Separating the amino acids in a protein is a hydrolysis reaction. This is where we use the parts from water to reform our amino acids. It needs an amine or an amino group and a carboxyl group, like so. And either of those 3 would be your correct answer to pick up the mark. So find the link, split the link, and then reform the amino acid to get your mark. Moving on, we're looking for hydrogen bonding. You need hydrogen to F, O, or N. And in these ones, we are talking about the parts here. You've got your slightly negative oxygen and slightly positive hydrogen, because oxygen has a higher electronegativity. And then we want a complete, it doesn't say what type, maybe a dotted line, a full line. Will it matter? Probably not. Let's go for patches. It has to be from the hydrogen of one of them to the oxygen of the other. We could have it that way, or you could have went and just did it that way. Probably that way shorter, but something like that just to show them there. Questions usually say like dotted or dashed, but here you've got the options. Moving on, we are separating the amino acids in a sample of collagen protein. Then we've got our solvent carrying the different amino acids distances in chromatography. They've given us the values for how far each of the amino acids travelled, and they've given us the calculation to work out this retention factor. Looking at proline, it says proline is 5.6. We now need to look at how far the solvent travelled. Distance from the solvent was 12. So 5.6 divided by 12 gives us our answer, which gives us our answer of 0.47. That would be that one there. It tells us that there are 4 amino acids present, but there are only 3 spots. When you look at this here, you can actually see it. They aren't exactly in the same position, but there's a bit of overlap. This must mean that the retention factors, the values for them, must be very similar. So 2 amino acids have similar RF values. F to R, baby F values. And this is shown because there's an overlap between the two of them for that. If they were fully on top of each other, then I would be comfortable saying they have the same retention factor. But here, because there's a wee bit of separation, then I would go for their similar. This one, predict which one has the smallest RF value. And it says up the top that the more polar, the shorter distance. So this is telling me that we need the most polar chemical. And here we're looking for differences in electronegativity. If we look at this part here, you can form hydrogen bonds from N to H between them. We've also got the O to H here. Got this bit. This bit. We've also got a carbon to oxygen bond, which would allow for permanent dipole to permanent dipole. However, they are the same in all of them, but this one also has a third position where hydrogen bonds could form. So it would be the most polar, and then that would be the one with the smallest value. So threonine, theronine, however you want to say it, would be the correct answer there. Number 5, why do people need fats and oils? Energy. They provide a lot of energy per gram. That'd be my answer there. Glycerol is propane 1,2,3 triol. The fact that I would recommend learning. 1, 2, 3 triol. Prop 1, 2, 3 triol. 3 OH groups. H here. H here. H here. H here. H here. And that would be answered there. To get a fat oil, we have glycerol, fatty acid, fat oil, and water. Glycerol is an alcohol plus acid from before, ester, and water. And that means that they will have an ester link in them. Next one, why fats have higher melting points and boiling points. And we can run this backwards from the one about linseed and olive oil earlier on, where if they've got higher melting points and boiling points, they must have stronger forces, which means they must be closely packed. Double bonds prevent the close packing. This must mean that they would be less or more saturated, less unsaturated. And then that's what they would want the 3 points. So fats are more saturated meaning their molecules can pack more closely together. This results in stronger intermolecular forces. You want to be specific, you could talk about LDFs and higher melting points. Maybe add in more unsaturated than oils, meaning they can pack closer together. Another one more closer together. Next one, fats and oils reacting with oxygen. Unpleasant flavour is when something goes rancid, so they're rotting fats and oils. It's not particularly nice. Next one, chemical test to tell these apart. They are both aldehydes because they've got a carbonyl group on the end. So that's no good to tell them apart. If one was an aldehyde, one a ketone, then yeah. But this one has got more, it has carbon to carbon double bonds. Molecule B will decolorize bromine water / solution. Or that one. Moving on, we're asked about free radicals. These are reactive species with an unpaired electron or unpaired electrons. So unpaired electron or electrons depending on the chemical. There are 3 steps in these ones. We have, first of all, an initiation reaction. We then have propagation, and then we have termination at the end. What can help tell these apart? If they're in order, then it's quite straightforward. Just remember in initiation, propagation, termination. If they're separated apart, in the first one, we've got no dots on the left, so no radicals. It goes to dots / radicals. Propagation will have them on both sides, so dots to dots. And then we've got dots to no dots in a termination for that. So the radicals have joined together. For that one, here we're talking about antioxidants which prevent oxidation from happening. How do free radical scavengers prevent chain reactions? They react with free radicals to form stable molecules. Next one, we're asked about why vitamin E is better than vitamin C for oils and fatty foods. I think we're leaning towards the whole non-polar, polar dissolving things perhaps. So vitamin E is got a long carbon chain. So this section here would be non-polar, just carbons and hydrogens. We've got bits of polarity here with the oxygens there, but if you compare it to this one, which has a lot more oxygens, so it'd be more polar parts, it's also got a smaller covalent carbon chain. I think that's what I'm going to go for. It is more non-polar, therefore more soluble in oils. What I'd go for there. Next one, here we're making salts, so this is a neutralization. And you want to replace hydrogen with metal. So it's the hydrogen of the carboxylic acid group. So the beginning bit will just be the same. 7COO. It's lost its H plus hydrogen ion. So it's going to be 2 minus, and then it'll be Na positive. Sodium's a metal and it'll be positive for that. It's which works in there. An advantage of a detergent is that it does not form scum. So using detergents will prevent the formation of scum. This one we have got to perhaps remember that it's 2-methyl buta 1,3-diene. For that, got 4 carbons in a row, double bonds in position 1 and position 3, and then you have a CH3 coming off of the second, and then you have the rest of your H's were appropriate for that, but that's the isoprene. Here, state the number of isoprenes in this. As I said previously, it's 5 carbon group. So we've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 3 isoprene units. Followed up by here, we have to write the name of this ester for that. So the foolproof way is just to draw it out fully. A wee bit long, but let's do it anyway. 1, 2, 3, 4, 5, 6. Then got the carbon. Now, an ester link is a C double bond O, but it could be drawn the other way round. What tells me which way around it is that this carbon has no hydrogens on it, so it would have to make a double bond with the oxygen to have its 4 bonds it needs to make, which means the other side must be where the O is for that. And then the side with the O here comes from the alcohol, and the other part's the acid, because a carboxylic acid is C double bond OOH. That 1 carbon from the alcohol means it was methanol, which gives us methyl, and then the acid had 1, 2, 3, 4, 5, 6, 7, 8 carbons in it, so octanoate would be the answer there. In this one, we have to draw a label diagram showing the method for preparing a catalyst. So the most straightforward way would be to use a boiling tube or test tube with a wet paper towel wrapped around the neck of the tube. So we have a wet paper towel acting as a condenser. We have a hot water bath. Not a Bunsen burner, because it'd go on fire, so we don't want that to happen. And then just say this is the reaction mixture. For that, you could use a heating mantle, just some sort of way it's not a flame would be the one you'd want to react them with. Next up, we have got a reaction with a catalyst. We're now asked to draw a dotted line to show what would happen without a catalyst for that. So typically we'd be drawing it when you add a catalyst and lower the activation energy. So without a catalyst, it would have a higher activation energy. So it would go up more steeply from that. From there, and come back down and join it on like so. So it has a greater activation energy there. Next one, why can this act as an emulsifier? It contains polar parts that can dissolve in water and non-polar parts that can dissolve in oil and fat. If you want to add more of the technical language, you could talk about them being hydrophilic polar sections. And then they would be non-polar or hydrophobic. Hydrophobic, non-polar, covalent sections. There are both polar and non-polar sections to this molecule. The hydrophilic polar sections dissolve in water, and hydrophobic non-polar parts would dissolve in the oil or the fat. So hydrophobic, hydrophilic. Emulsifiers are made from oils by reacting with glycerol. Compare the energy released by different types of biodiesel. One variable needs to keep the same in both experiments to make a fair comparison. The one thing that can make a difference is how far away it is from the container. So distance from container to the burner. That it doesn't have to be the mass of water because it's EH equals CM delta T. So it takes into account if you've got more or less water. So it wouldn't be that. Heat shield, if there's a draft shield to prevent heat escaping to the surroundings, which isn't demonstrated here. There'll probably be some other ones as well. My eye was just drawn to the next question, which is suggest an improvement to prevent heat loss to the surroundings. Use or insulate the apparatus with a draft shield. I have something around it which prevents as much heat being escaped. Moving on. Here we're asked to calculate the energy released when 1 gram of biodiesel was burned. EH equals CM delta T. EH equals, it's the specific heat capacity of the water being heated, so 4.18. It's the mass of water, not this one. So it would be times 0.2 because we want it in kilograms. Yep, and then it's going to be times by the difference between those two is 21. 4.18 times 0.2 times 21 gives us 17,556. That was when we burned 0.420 grams, gave off 17.556. Question wants to know how much would we get from 1 gram. All these kind of proportion questions, we need to think, is it going to be more than 17.556 kilojoules or less? Well, if we do, to here, we've got to end up with a bigger number here. Any number divided by itself gives you 1. So if I take the other side and do 17.556 divided by 0.420, I should end up with a number bigger than itself. That divided by 0.420 giving me 41.8 kilojoules per gram. Okay, next one, we are asked about cost to produce E20 fuel. Cost of biodiesel to produce 75 litres of that. So first thing I'd spot is that it's 20% biodiesel. If I work out 20% of 75, now on your calculator there will be the percentage button. If you do that times 75, it will give you the answer. In my calculator on my computer, it's just the more simplistic one. So 20% is 20 out of 100, percent out of 100, times 75 gets me 15 litres. So we are going to need 15 litres of biodiesel. And then to get the cost, it tells us that 1 litre is 85 pence. So 15 litres is going to be 15 times bigger. So then when we do 0.85 times 15, we get £12.75. That would be our final answer there. If the calculation came out to say 12.7 as an answer, you should still show it as an appropriate price with the 2 decimal places for the pennies we've got for that one as well. But here it's nice and straightforward. Round it to get 2 decimal places would give you there. Next one, we've got a calculation that they've just given us. We're not expected to know this, but we are asked for the concentration. Well, if salinity equals concentration times 0.018066, then concentration equals salinity divided by 0.001866, which for us is 35 over 0.001866. That gives us 19373. And importantly, this is in milligrams per litre. Our question doesn't want milligrams per litre, they want grams per litre. Couple ways of changing them. One thing to note is that 1 gram equals 1,000 milligrams. A milligram's 1,000th of a gram. So to go from milligrams to grams, we can divide by 1,000. And that would give me 19.4 or 19.3 grams per litre. 19.4 for that. The prefixes are also in the back of the data booklet, where they tell you the conversion factor. So it's got for milli is times 10 to the minus 3. And if you took our answer of 19,373 times 10 to the minus 3, does give you 19.373 rounded to 19.4. You just need to memorize the definition. It's a solution of accurately known concentration, followed by how you use a pipette. You first rinse it with the substance that you're using it with. So first rinse with seawater. And then you want to fill to mark. And you always read from the bottom of the meniscus, the bottom of the little bubble on top of the liquid. And this question here, an indicator is used to identify the end point, so you can see when the reaction is finished. Next one, when you're dealing with an average titer, it's to do with concordant results, which are within 0.2 of each other. Those two are, the top one isn't. So sample 1 is not concordant. That. Next one, we're doing a calculation to work out the concentration of chloride ions. So on the right hand side, we're finishing with chloride ions, and we're going to do C equals N over V. And we're starting off looking at our silver. It says it's a 1-to-1 ratio, which means it will just be the same number of moles on both sides. I'll just set it up first of all. So our volume of silver nitrate is 11.55, which we want it in litres. So N equals CV, so N equals something times 0.01155. And then they should give us a concentration, which they do, 0.5. Now at this point, it would probably come up in your calculator as 5.775 times 10 to the minus 3, which would probably make it be easier in this question. It's going to be the same on both sides, so 5.775 times 10 minus 3 on both sides. So in concentration equals that number divided by the volume of chloride ions in seawater. And that, even though it doesn't say chloride, it doesn't say chloride there, but chloride is in the seawater. So we're using the 10, which would become 0.01. And then when we pop that in, popping that into our calculator gives us 577, gives us 0.5775, which I'd probably round to 5.78. Moving on, they're telling us we've got a different number of we've got a different number of moles in a different volume, and we want the mass of 1 litre. That right, I'd probably deal with 1 litre first, because if 0.00492 moles is in 10 centimeters cubed, well, a litre is 1,000 centimeters cubed. Then I want to times that by 100, so it would be 0.492 moles of chloride ions. And then to work out the mass, M equals N times GFM. Importantly here, it's chloride, so Cl negative. It is not chlorine, which would have been Cl2. So we're just using 35.5, the GFM of chloride, not 71 for that. So 35.5 equals, and here 0.492, 35.5, 17.5, let's go for 17.5 grams would be my final answer. Next one, we have to compare this chemical to water. They have both got polar bonds because they've both got a difference in electronegativity. They are both polar molecules because they're both non-symmetrical. Polar bond, polar molecule, polar molecule. Now, the reason this is important is this means they will have either permanent dipole to permanent dipole interactions or hydrogen bonding. Number one, water has H2O. Water can form hydrogen bonds. Chloromethane does not have hydrogen to fluorine, oxygen, or nitrogen, so cannot make hydrogen bonding. So, chloromethane will have permanent dipole to permanent dipole interactions between its molecules. And these are weaker than the hydrogen bonding in water. Here we've got equilibrium question. And it's a using your knowledge of chemistry question. Okay, we're talking about yields and reversible reactions for that. Reversible reactions can reach equilibrium where the forward and backward reaction rates are equal and the concentrations will remain constant. We could add catalyst to the reaction, and the catalyst would not affect the position of equilibrium. We wouldn't move it left or right, but you'd get to that point faster. If you added a reactant or removed a product, this would shift the equilibrium to the right, making the forward reaction happen more quickly. On the other side, if you removed a reactant or added a product, that would shift the equilibrium to the left for that one. If you were to increase the pressure, that will favour the side with the lowest number of moles of gas. Looking at your experiment, you can decide if high or low pressure is preferable. And then decreasing the pressure would favour the side with the highest number of moles of gas. Only gases are compressible, so we don't care about liquids or solids. If you increase the temperature, that would favour the endothermic reaction, which would be shown by a positive enthalpy change. Endothermic reactions cool their surroundings and are favoured by an increase. On the flip side, decreasing the temperature would favour the exothermic reaction, and an exothermic is shown when you've got a negative enthalpy change. For that. You could also add the cheaper reactants in excess to ensure they get the maximum yield out of your chemicals. On to number 9. Here we are asked to calculate the mass of chlorine required to react with 1600 kilograms of titanium oxide. So I'm going to start with titanium oxide over here. N equals M over GFM. I'm going to put it into grams, even though it's going to make it a wee bit more unwieldy, but it's the gram formula mass we're using, so I feel more comfortable using this. And that is 79.9. So N equals and that gives me 20,025. Going between two chemicals, we want to use our ratio. It's a 1:2 ratio. We need to double our 20,025 to be 40,050. Finally, we want our mass of chlorine. This time it's 71 because it's diatomic chlorine, not chloride. So M equals N times GFM. So M equals 40050 times 71. And this is how many grams it would be. And it wants it in kilograms, so now divide it by 1,000. So we would have 2843.55 kilograms. We could have just left it as kilograms at the start and at the end. Because it's gram formats, I prefer to have it in grams just so it lines up a bit nicer. Next one, we have liquid at room temperature. We're looking at titanium chloride. When we look at the electronegativities, there is a difference. As I said earlier, it's not the biggest difference, or it's like halfway between 0 and the biggest difference. So it's likely to be covalent. It's a liquid at room temperature. That suggests that it's going to be a covalent molecular substance. The networks have high, ionic have high melting points and boiling points. So it would be more likely to be a solid at room temperature for those ones. Covalent molecular for that one. Atom economy we get from the data booklet. Mass of desired product over total mass of reactants. One common mistake people make is forgetting to involve the balancing numbers. The desired product is titanium. And there's one titanium, so it's going to be 47.9 on top. Over, well, the titanium chloride is 189.9. We have to add on 2 times 24.3. And then you want to times that by 100. Gets us to 20.1% atom economy. That one. Next one, we want the oxidation ion. We want the ion electron equation for the oxidation of magnesium atoms. I would go to page 13. Magnesium is shown here. This is the reduction reaction where it's gaining electrons. Therefore, for the oxidation, it's the opposite way round, where we have our solid magnesium losing electrons to become magnesium ions and electrons. Next one, we're talking about reacting two things together. And they should give us a ratio. Yes. It's a 2 to 1, a 1 to 2 ratio. So TiCl4 Mg, a 1 to 2. Now, before we can compare them, we need to work out how many moles of each of them that we've got. So I'll do that over at the side. So N equals M over GFM. So it'll be that many grams over 189.9. And then for the magnesium, it's going to be that over 24.3. Okay, now got both our moles. So there's two possibilities. First thing we could do is to use all TiCl4. So I've worked out that I've got 10,005 moles, which would mean I'd need 20,010 moles of magnesium, which I do have enough to make that happen. For that, we have the bigger number, so we have 3864 moles. The ratio tells us we use 20,010. So excess is the difference between those. So 30864 take away 20010, and that will give us 10,854 moles in excess for that one. Here, why would you do a reaction in argon? Well, argon is an unreactive substance. Asked here about which one would be preferable. Number one, it's a lower temperature than we had in the other one. Or there's less waste, only one waste product. That will result in a higher atom economy. Last question is a drop-down question from Advanced Higher Chemistry, where they're describing how a technique called NMR works, and they're talking about each line represents a hydrogen environment, and the height is related to the number of hydrogen atoms in the environment. And it's found on page 17 of the data booklet. So use the data booklet to find the chemical shift value of the hydrogen atom in this environment. Now, with these ones, what we need to look for is it's the one in bold that's got the shift shown in here. So we're looking for one that has carbon to carbon double bond. Shuffle, 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 shuffle. We're looking like we're down in here. We are somewhere. We're looking for 6 to 4.5 for that one, because it's showing that is for that hydrogen in particular for that. So it's 6.0 to 4.5. And this one here, we're showing the NMR for a compound that's C3H6O, and we're asked to work out which type of chemical we have got. So it's got a shift of 2.2, roughly speaking. Let's go and look at what those could be. Running them down, there's quite a few we could rule out. Starting from the bottom, well, it's got oxygen, not nitrogen, so it can't be that one. It's got oxygen, so it cannot be this one. Again, none of them have oxygen, none of them have oxygen. Oxygen comes in for aldehyde, ketone, acid, or ester. With C3H6, your two potential options would be propan-al, where the double bond O would be here, or propanone, where the double bond would be in the middle. In the first one, there would be 3 different environments, because this is a hydrogen right beside a C double bond O. You've got a CH2 between C double bond O and a CH3, and then a CH3 beside a CH2. Whereas in this one, both of the ends are right beside a C double bond O. So this means that our chemical would have to be propanone. Last question asks us to draw the spectrum for this particular chemical. So first of all, we need a shift at 1 for the CH3. There are 3 hydrogens in CH3, so it would go up to a height of approximately 3. And then the other one, we want to go to 3.7, so 3.5 would be there. So 3.7 is 2 little boxes past that. There. And that would come up to a height of around 2, because it's CH2 versus CH3. And that's all shown from up here. The fact that CH3 goes up to 3, and then just one H goes to 1, and ours were 3 and 1. That brings us to the end of the question and the end of the paper. Thanks for watching. Goodbye.